Hello everyone, welcome back to my channel. My dear friends and students, we will continue the derivation, which is application of variation principle to helium atom. So let's continue the derivations. So yes, in the previous video we have found the Hamiltonian and the wave function, and we know the Laplacian operator for the first electron and for second electron. Now we will solve the integral one by one, which I have mentioned in equation 4. Okay, so let me write the expression for first integral. I'm representing it by I1. So I1 represent first integral, which is equal to minus 1 by 2 double integral psi star del 1 square psi d21 and d22. Now we know the value of psi star and psi. So it's a wave function for helium atom, which is equal to, let me write the expression. So psi equals to z cube by pi into e raised to power minus z r1 plus r2, right? So this expression we will substitute here, and the expression for del 1 also we will get minus 1 by 2 del square, double integral psi is z cube by pi Here I will write the expression for del 1. Del 1 is 1 by r1 square, curl by curl r1, r1 square, curl by curl r1, again psi. Psi is z cube by pi, e raised to power minus z, r1 plus r2, then d21 and d22. So student, here we know d21 and d22 is the volume integral over the whole space, and we know in the polar coordinates d21 equals to 4 pi r1 square d r1, and d22 is equal to 4 pi r2 square d r2. Okay, so we will substitute d21 and d22 by these expressions or these values. So here I will write, in place of d21 we will write, I'll write the same expression again. Here you can see z cube by pi, it is 2 times. So I will write the square of this expression. And e raised to power minus z, r1 plus r2, 1 upon r1 square, curl by curl r1, r1 square, curl by curl r1, this exponential function. I have split the exponential function into 2 parts. So here I'm writing 4 pi r1 square d r1, and here I'm writing 4 pi r2 square d r2. Okay. Now student, this r1 will be cancelled out with this. And now I will take out all the constant terms outside the integration sign. So here we have z cube by pi whole square And we have this 4 pi 2 times. This is also constant term. So I'm writing 4 pi whole square here. Okay, inside the integration sign, we have exponential. This also I'm splitting into two parts. And here we have curl by curl R1 square, curl by curl R1, exponential minus Z R1. Okay. This exponential part I'm writing outside because it is constant with respect to R1. And what else is left? dr1, r2 square, dr2. Now, student, we will separate the integral. Here we have two integral. One first integral for the first electron and second integral for a second electron. So I will separate the integral. This is z6 by pi square. This is 16 pi square. And I'm writing the first integral. Limits will be from 0 to infinity. I'm writing the terms containing R1 in the first integration. ZR1, curl by curl R1 square. And here I am differentiating the exponential with respect to R1. So I will get e raised to power minus ZR1. And differentiation of the power also will get minus Z. Okay. And we'll write dr1. Then we'll write second integral again from limit from 0 to infinity. And here we have two exponential, this first and second. Okay, so we can combine it. We'll get here, we'll get minus ZR2. Also, we have R2 square that I'll write over here into dr2. Okay, so now we will solve these integrals one by one. So student, the second integral here we can solve it by using the standard integral result. We know that the integral of x raised to power n e raised to power minus ax dx equals to n factorial a raised to power n plus 1. Okay, so this is second integral we can solve by using this standard integral, right? So you can see if you compare this integral with the standard one, here n is equal to, here n equals to 2. Okay, n equals to 2. So what result you will get here? So you will get 2 factorial over a. What is a here? A is the coefficient of x. And here we have, sorry, 2z, I know. Yes, so here we have 2z. A equals to 2z. So 2z raised to power 2 plus 1, which is 3. So this result we will get for the integral, right? So I will write the result in the next step. Yes. So here I will write the result 1 by 2. Pi square will be cancelled out. And here we are left with 16z6. Okay. And inside we have 0 to infinity e raised to power minus zr1. Again, we have differentiation. Here we have minus z, right? So minus z I'm writing here. Okay. Also, yes, just wait a second. Let me erase it. So here, which term is left? R1 square e raised to power minus ZR1. Okay, dr1. Now, in place of this integral, we will write the result 2 by 8z cube. Here we will close the bracket. Now we will move to the next step. Let's see what is the next step. So next step is we will write all the constants term outside the integration sign. So here I have minus 1 by 2. or you can write 16z6. This minus z also we will write outside. 2 by 8 8z cube also we will write outside the bracket, outside the integration sign. Now inside we have 0 to infinity e raised to power minus z r1. Okay, so here we have differentiation of two functions. We will differentiate it by parts. Okay, so let's start the differentiation. So first function will write as it. I'm writing second function as it is. I'm differentiating the first one, which will give us 2r1 plus first as it is will differentiate second e raised to power minus z r1 into minus z. So this will be the differentiation and dr1. Close the bracket. Now write the next step. So we will cancel out the terms. Z cube will be cancelled out. This minus minus will be plus. 2 will be cancelled out. And the 16 also will be cancelled out with 8. So we are left with 2. Here we are left with z power 4. And now we will solve it. E raised to power minus z r1. We have 2 r1 e raised to power minus z r1 minus z r1 square e raised to power minus z r1. So students, now we will multiply the exponential. Okay. We will multiply this exponential with break inside the bracket with both the terms. And with this, we will get again two integrals. So 2 is constant, I'm writing outside. Here I have r1 e raised to power minus 2z r1. Okay. Then minus 0 to infinity z r1 square e raised to power minus 2z r1 dr1, sorry, dr1 here also. Again, we will differentiate it by using the standard integral. Okay, so I will write the results directly. We know the results. Okay, so 2 into here n value is 1, so 1 factorial over a is 2z raised to power 2. Similarly here n value is 2, you can see power is 2, so n is 2 factorial divided by 2z raised to power n plus 1, which is 3. Okay, so we will solve it and let's see which result we are getting. So by 2 by 4z square minus 2z by 8z cube. So we will cancel out the terms. 2z power 4 multiply by 2 by 4z square minus we are left with 1 by 4z square. Okay, so we will further solve it. We will get 2z4 multiply by, subtract these terms, we will get 1 by 4z square. And after cancelling the terms, we get z square by 2. Yes. So I1 first integral equals to z square by 2. Students, we got the result for integral 1. Similarly, we will solve the integral 2 and same result we will get. Okay. So there is no need to solve the second integral because we will get the same result. So similarly, you can write similarly I2 equals to z square by 2. Okay. No need to solve it. Because by using the same step or same procedure, you will get z square by 2 result. Now we will solve the third integral. Okay, and the result of third and fourth will be same. So we'll solve the third integral. I3, which is equal to a minus 2 double integral psi star 1 by R1 psi d tau 1 d tau 2. Okay. So here we will substitute the expressions for psi star. Psi star we know it is e raised to power. Wait. This is yes. So psi star we know it is z cube by pi, right? And exponential e raised to power minus z r1. I'm splitting the exponential part. Then 1 by r1. Again wave function z cube by pi. Okay, exponential. Again I'm splitting the exponential. All right. And we have d tau 1 which is 4 pi r1 square and 4 pi r2 square dr1 dr2. Now again we will take out all the constant terms outside integration sign. We have this factor 2 times. So we'll write z cube by pi whole square. Also we have 4 pi 2 times. We'll write 4 pi 2 times. And here we have r1 square, here we have r1 that will be cancelled out. So in the integration, we'll write here I'll split the integration also. In the integration sign 1, we'll write all the terms containing r1, and integration 2 will write all the terms containing r2. So I have r1 e raised to power. This we have 2 times, so we'll add it. We'll get 2zr1 dr1. Similarly, we'll write for second integral r1 square e raised to power minus 2zr2 dr2. Okay. Yes. Now we will solve the integral using standard integrals again. Minus 2 into z raised to power 6 by pi square, 16 pi square. Here we will solve the integral. We get here power is 1. So 1 over 2z raised to power 2 into, here we have n is 2, that means 2 into 2 factorial of over 2z raised to power 3. So this we are getting. Now we will solve it. Simplify. We will get minus 2 into z6 by pi square into 16 pi square into 1 by 4z square into 2 by 8z cube. Okay. So here we have z5 will be cancelled out. Pi square will be cancelled out. And this will be cancelled out. We'll get 2. 2 8 is 16. This will also be cancelled out. We are left with minus 2z. Yes, so we are getting minus 2z for third integral. Similarly, fourth integral will also give us the same result. So no need to solve the fourth integral. We will we will write that I4, that means the fourth integral, similarly fourth integral also equal to minus 2z. Okay, now last integral is left, I5. Okay, last integral is it is double integral psi star 1 by r1 to psi d2. So my dear friends and students, we will not solve this integral because it is quite tedious and it is complex to solve. So we will use the result. Okay, we will directly use the result. So after solving this integral, we get 5 by 8z. This value we get for the fifth integral. Okay, so you have to remember this, the result for fifth integral, that is 5 by 8 into z. Now we will substitute all these values in our equation number 3, I think. Let me show you. So these values we will substitute in the energy equation. Let me show you, please wait. Yes, here. Here in the fourth equation. Okay, so we will substitute the values of all the integral in equation number 4. Just give a second to me. Yes. So here we will substitute all the values for all the integral. That will give us E equals to, the result for the first integral was equal to z square by 2. For second also z square by 2. For third it is minus 2z. Fourth it is minus 2z. For fifth it is 5 by 8z. Right? So after solving this, we will get the expression for E. So let's see what is the expression for E. So it is z square by 2 and z square by 2. We will add it and we will get z square. Right? And after this, we will solve the third, fourth and fifth term. So we will get, it is minus 4z plus 5 by 8 into z. We will solve it by using the LCM. So after taking the LCM, it will give you 27 by 8z. 27 by 8z. Okay. So here we got the expression for E. Right? Which is equal to z square by 27 z by 8. So now you see the expression of energy, it contains some variational parameter, that is z. Okay, so in order to get the value of energy, ground state energy for the helium, we should know the value of z. So how we will get the value of z? So in order to get the value of z, we will differentiate curl E, we will differentiate energy with respect to z, and then we will put it equals to 0 in order to minimize the energy. So differentiate curl E, differentiate E with respect to z, you will get 2z minus 27 by 8. Then put it equals to 0. After putting it equals to 0, you will get the value of z, which will be equal to 27 by 16. Okay, so now this value we will substitute in this equation, in energy equation again, which I have mentioned above. So E will be equal to z square, which is 27 by 16 whole square, minus 27 by 8 into 27 by 16. So after solving this expression, we will get minus this value. We will get minus 2.84. But this value we are getting in atomic units. Okay. Because we initially in the derivation, we have assumed all these parameters in atomic unit. That's why we are getting this result. Now, in order to get the energy in electron volt, we will use the relation between one atomic unit and the electron volt, and that is equal to 27.21 electron volt. Okay, so we will substitute, we will convert the unit by multiplying 2.84 by 27.21, and finally you will get the final result 77.48 electron volt. Okay, so this value, this is the ground state value of helium atom. that we are getting from the trial wave function using the variation methods. So here we have completed the derivation. Thank you so much for your patience and watching the whole lecture. Thank you so much.